So for line compensation, let's consider a line which is loaded at its surge impedance loading level. In this case, we should expect a voltage profile that is flat. The voltage at the sending end is equal to the voltage at the receiving end. But in case of light loading or no load, we should expect a rise of voltage at the receiving end, while in the opposite case where we overload the transmission line above the SIL, we should expect a drop of voltage. Let's, for example, here rated load, we have a drop of voltage, and this drop of voltage drop will increase with the loading level. So for these two cases, no light loading and overloading, it will require different compensation solution. For the light loading, we should think about inserting a shunt reactor with a transmission line, while for the heavily loaded case, we should use shunt capacitors, static VAR control, and synchronous condensers to improve the voltage and increase the power transfer and improve the system stability. So for the shunt reactor, which is used for light loading, it is shown in figure 5.7 how it is connected to the transmission line, while IR is VR divided by the impedance of the shunt reactor. And it's very important to observe the effect of the compensation. See here the uncompensated line, how the rise of voltage at the receiving end is very, very high, while for compensated lines, the receiving voltage level is similar or very close to the voltage level at the sending end. For the shunt capacitor compensation, usually we should install shunt capacitors for high loads with lagging power factor in order to compensate for the reactive power. So the capacitor bank will provide sufficient reactive power to maintain the receiving end voltage at satisfactory level. The capacitors can be connected directly to the bus bar or to the tertiary winding of the main transformer, and are disposed along the route of the transmission line to minimize losses and voltage drops. Here we will be calculating the angle delta first using equation 5.85. And then we calculate, thanks to delta, we calculate the reactive power after compensation. And after that, we calculate the compensating reactive power, the reactive power needed by the compensation unit or the shunt capacitors in order to maintain the receiving end voltage at the desired level. So this is the principle of shunt compensator compensation, and we will continue later on with an example.